A rocket of mass m is fired vertically from the surface of the Earth, which is at r1, where r1 is the distance from the center of the Earth to the surface of the Earth, assuming that no mass is lost, for which we can be very grateful. As it travels upward, determine the work it must do against gravity to reach a distance r2. The force of gravity is capital G, which is the gravitational constant, times the mass of the Earth, times the mass of the rocket, divided by r squared, and the force of gravity points towards the Earth, so this force, if you write it as a vector, is pointing in the negative r hat direction. Okay, now maybe I should have mentioned this in the previous problem, but 82 and 83, I think, are probably the only problems in this book where we cannot say the force of gravity is equal to the mass times little g. And because we cannot say this, we also cannot say that the gravitational potential energy is equal to the mass times little g times h. So instead, we have to integrate to find the work done. So we're going to use equation 14.1, where the work is equal to the integral of f dotted with dr as we go from r1 to r2, and we actually are going from r1 to r2 in this problem. Okay, now this says find the work done against gravity, but if I put the force of gravity in here, this is going to be the work done by gravity. Okay, so the object the rocket is moving this way, and the force of gravity is pointing towards the center of the Earth. And so if I find the work done by gravity, the dot product there is going to be negative. But I'm actually asked to find the work done against gravity, and so that quantity is going to have the opposite sign of the work done by gravity. But I'm just going to go ahead and calculate this first and worry about the sign afterwards. Okay, so this is the work done by gravity, and it's the magnitude of the force of gravity, which is G times ME times M divided by R squared times dr. Now we have been saying that the magnitude of dr is ds, but actually in this problem it makes sense to keep the magnitude of dr as dr because that's r. Okay, so this is the magnitude of the dot product, and then I get a negative sign because the force of gravity is pointing in the opposite direction of the displacement. I'm going from r1 to r2. I can pull out the capital G, which is the gravitational constant, and the masses. So then I'm just integrating 1 over r squared with respect to r. And that would be r to the negative 2 if you write it in the numerator. We have to raise the power, so that becomes r to the negative 1, or 1 over r, and divide by the new power, which is negative 1, and so that cancels out this negative sign here. As we go from r1 to r2, so the work done by gravity is, well, I guess I'll write it as this, minus 1 over r1. Now, we're going to consider the signs. So, first of all, should the work done by gravity be positive, or should it be negative? So if the force is pointing towards the Earth and the rocket is moving away from Earth, the work done by gravity should be negative. But at first glance, what I have here looks positive. So let's just make sure that we're actually getting something negative. So R2 is greater than R1. So 1 over R2 is less than 1 over R1. So I'm going to rewrite this as minus G times the mass of the Earth times the mass of the rocket, 1 over r1 minus 1 over r2. So because r1 is smaller, 1 over r1 is greater than 1 over r2, so now the quantity that I have in parentheses is positive, so the work done by gravity is negative. But if I want to find the work done against gravity as the rocket goes from r1 to r2, this work would be done by another force, and that force would be pointing in the opposite direction, and which would be in the same direction as the displacement, so that would be doing positive work. So I should have another force in my free body diagram here. So if the rocket is starting from rest and the force of gravity is pointing towards the center of the Earth, you must have another force pointing in the opposite direction. Otherwise, your rocket isn't going to be launched. So let's call this FR, I guess, for the force of the rocket. That would be the force of the thrust. So if the rocket accelerates in this direction, then the force of the rocket is going to be greater than the force of gravity. And because so let's see. The work done by this force is probably going to be greater than the work done by the force of gravity, because we have, let's say the rocket's starting from rest, so this would be 0. And let's say, we'll ignore the gravitational potential energy because we're looking at the work done by the force of gravity. So let's do, can I do it? Yeah, let's just look at this equation here. So I have the work done by all of the forces, which would be the force of the rocket and the force of gravity. So if I want the final kinetic energy to be greater than the initial kinetic energy, then this force is going to have to do more work than just what I found here, and that extra work is going to give you your extra kinetic energy at R2. But the work that we have to do the work that we have to do against gravity would just be the same magnitude that we have here. So this is same magnitude, but opposite sign. So that's the work done by this force to overcome gravity. And that is the answer.